Hello मेरे प्यारे बच्चों. I know, exams are right around the corner and this D and F block chapter, it can look a bit scary, right? But बिल्कुल चिंता मत करो. Don't you worry. We're going to revise this whole thing together and I promise you'll see how super easy it actually is.
So take a nice deep breath. No tension allowed here. Your favorite tutor is here to make everything crystal clear. All the important concepts, one by one. By the end of this, you'll feel so much more confident. So, shall we begin? Let's do this.
Okay, so first things first. Who are these D and F block elements? Just look at your periodic table. You see that big block of elements sitting right in the middle, from groups 3 to 12? Those are our D block elements. You can think of them as the middle benchers of the periodic table class. And what about those two rows kept separately at the bottom? Well, those are our F block elements, our backbenchers.
Right. Now, let's jump into our first very, very important concept. And listen carefully, because examiners just love to ask this one. What exactly is a transition metal? You have to know the official definition for this.
So here's the deal. The official IUPAC definition says that transition metals are elements that have a partially filled d orbital. Now, what does that mean? Imagine the d orbital is a Tiffin box with 5 compartments. For an element to be called a transition metal, this Tiffin box must be incomplete. So not totally empty and not completely full. Got it? This is a classic 1-mark question, so remember it well.
But this brings up a very interesting question. It's another exam favorite. If these elements are sitting there in the D block, then why are poor zinc, cadmium, and mercury not considered true transition metals? Why aren't they part of the cool kids club? Any ideas?
And here is the answer. It all goes back to our definition. It's because their d orbital Tiffin box is completely full. They have a D10 configuration, which means all 10 spots are filled. And this is true for the atom and for their common ions, like zinc 2+. Since that d orbital is never incomplete, they just don't fit the definition. Simple as that.
Now, let's talk about 2 special cases, chromium and copper. You see, atoms love to be stable, and they become extra stable when their orbitals are either exactly half-filled or completely filled. Think about our Tiffin box again. It just feels more balanced when it's half full or completely full, right? So look at chromium. We expect it to be 3d4, but it's clever. It borrows 1 electron from the 4s orbital to become 3d5, a stable, half-filled configuration. Copper does the same thing. Instead of being 3d9, it borrows an electron to become 3d10, a super stable, fully filled d orbital. This is a very important exception to remember.
All right, now for the really fun part. Why are these metals so special? Well, because they have some amazing properties. I like to call them their superpowers. Let's check them out.
Superpower number 1, they can show lots of different oxidation states. They're like chameleons, always changing. Just look at our hero, manganese. It can show every oxidation state from +2 all the way to +7. Wow. And why can it do this? Well, it's because the energy difference between the outer n electrons and the inner n-1d electrons is very, very small, so it can lose electrons from both shells easily.
Next superpower, they make beautiful, colorful compounds. Just think about the lovely blue color of copper sulfate. It's so pretty, isn't it? Now, if the examiner asks you why, you just have to write 1 magic phrase. Ready? It's DD transition. That's it. That's your answer. An electron jumps up to a higher energy d orbital, and the color we see is the light it gives off when it comes back down. Just remember the term, and you'll get full marks.
They're also brilliant catalysts. You know, they help speed up reactions without getting used up themselves. How do they do that? Well, have a look at this example from your textbook. Iron 3 helps iodide and persulfate react. First, it takes an electron from iodide and becomes iron 2. Then it gives that same electron to the persulfate and boom, it's back to being iron 3 again. And this cycle just keeps on repeating. So cool. And last but not least, they're magnetic. So if a substance has unpaired electrons that are single in their orbitals, it gets weakly attracted to a magnet. We call this paramagnetic. But if all its electrons are paired up, it gets weakly repelled by a magnet, and we call that diamagnetic. Basically, the more unpaired electrons an atom has, the more magnetic it is. Okay, bachon, full focus now. We're moving on to the 2 VVIP compounds of this chapter, potassium permanganate and potassium dichromate. I can almost guarantee you that you will get a question from this section, so pay very close attention.
First up, potassium dichromate. How do we make it? It's a simple 3-step recipe. You start with something called chromite ore. Step 1, you roast it with sodium carbonate, and you get a yellow-colored solution of sodium chromate. Step 2, you add some acid to this yellow solution, and it magically turns orange. This is sodium dichromate. And for the final step, you just add potassium chloride, and the beautiful orange crystals of potassium dichromate separate out. See? 1, 2, 3.
Now listen, if you want some guaranteed pakka marks in your exam, you absolutely must practice drawing these two structures. You can see on the screen, the yellow chromate ion is a simple tetrahedron. And the orange dichromate ion, array, that's even simpler. It's just two of those tetrahedrons joined together, sharing one oxygen atom at the corner. Please, my dear bachcho, draw this a few times. It's very, very important.
Next, our second hero, the famous purple-colored potassium permanganate. Its preparation is even easier, just 2 steps. First, you take manganese dioxide and cook it with potassium hydroxide. This gives you a green compound called potassium manganate. Then you take this green solution and pass electricity through it, and voila! You get your beautiful dark purple potassium permanganate, from green to purple.
Now, the most important property of KMnO4 is that it's a super powerful oxidizing agent. It's like the debunk of chemicals. But remember, its power changes depending on whether the solution is acidic, neutral, or alkaline. For your exams, just remember one important reaction for each condition. In acidic solution, it changes iron 2 to iron 3. In neutral solution, it changes iodide to iodate. And in alkaline solution, it changes thiosulfate to sulfate. That's all you need.
All right, we've pretty much mastered the D block. We're almost at the finish line. Let's just take a quick peek at our backbenchers, the F block elements, also called the inner transition elements. For your exams, you don't need to know every little detail here. Just the basics and the main differences will do. The best way to learn this part is with a simple comparison. Look at this table. For lanthanoids, the 4F orbitals are being filled. They mostly just show a +3 oxidation state, and they are not radioactive. Well, except for one. For actinoids, the 5F orbitals get filled. They show a huge range of oxidation states, and, this is important, they are all radioactive. Just remember this table, and you are sorted for this topic.
You have all been listening so well. Now, let's put all that knowledge to the test. It's time for our Pakka Marks rapid-fire round with some common exam questions. This will really boost your confidence. Ready? Let's go.
Okay, first question for 2 marks. Why do transition metals mix and match with each other so well to form alloys like steel or brass? Come on, think about it. What is similar about them? And the answer is because they are all almost the same size. Simple. Since their atomic radii are very, very similar, the atoms of one metal can just slip in and replace the atoms of another metal in its crystal structure. It's like trying to fit similar-sized marbles into a box. Easy peasy. Okay, next question. This one for 3 marks. This is a classic board exam question. What happens when you add our orange friend potassium dichromate to a solution that has iron 2 ions? And don't you dare forget the ionic equation. So what happens is that the orange dichromate ion oxidizes the pale green iron 2 ions into yellow-brown iron 3 ions. And in this process, the dichromate itself gets reduced to the green chromium 3 ion. And that's why the final solution turns green. And there on the slide is the all-important ionic equation. Please, please, I'm requesting you, practice writing and balancing this one a few times. And that's a wrap. See? That wasn't so difficult, was it? We've just revised all the most important concepts from this chapter, and you did a fantastic job. You are so well prepared now. Go and rock your exams. You are going to do wonderfully. All the very best, my dear bachchon.